Hello, I'm Shyam, and today we're going to go over integrated rate laws for AP as a review, we already learned the differential rate laws. So, furthermore, as another review, zeroth law, first law, and second law. Let me redraw some of the numbers real quick. Then, yeah. I'll move this to the right a bit. But basically, zeroth law, this is when concentration has no effect. So the rate law is just k times e to the zeroth power, or this is the same thing as just saying k. First order, if we multiply the concentration by x, you'll multiply the rate by x. So like if it doubles, this doubles. If it triples, this triples. So the rate is just k times the concentration to the power of 1. You don't need to power that because anything to the first power is just itself. Second order is if we multiply the concentration by a number, the rate will be that number squared. So if we double it, this will quadruple. If we multiply the concentration by 3, the rate will increase ninefold. So K times concentration squared. So basically, we are able to find the rate given the current concentration. And the rate is basically how fast the amount of concentration is changing. So this is useful when we know the current amount of concentration and we want to find how fast the the concentration is disappearing, because this is the reactant. Remember, this is the rate of disappearance. But the problem is, what if we have a given time? So like, what if we want to try finding how much concentration is left in 5 seconds? Well, after 5 seconds after the reaction. Well, this equation doesn't really help. This just tells us how fast the um, the concentration is disappearing at a given time. So that's why we need to turn to integrated rate laws. Integrated rate laws are basically corresponding concentration time t, so at a given time, um, versus time. So concentration versus time. Right now we know the rate, but we want to find a way to change these rate law, differential rate laws into integrated rate laws. And what normally you would use calculus for this, but the AP Chem test, it doesn't expect you to know calculus, so it just gives you the reaction, the equations for the integrated rate laws. But it's nice to have like a small bit of understanding of how these laws are derived. So rate is basically change in concentration over time. So change in A over change in time. So if it's zeroth order, you're basically saying change in concentration over time is equal to K. But mathematically speaking, you're actually losing K every second. So change in time, it's going to be negative K. The rate is going to be negative. I know that rate and negative doesn't like make sense, but in mathematical terms, if you look at a graph, you're actually losing concentration over time because it's a reactant, right? You're not gaining more reactants as the reaction goes on. The reactants are being converted to products. So basically, from here, um, you use some calculus to essentially just integrate both sides, and then you would get something like um, negative KT, and then you have an initial condition and so on. But basically, after some math, you're able to get these differential laws. And once again, you do not need to know the math required to like derive these laws. But it's basically a quick summary of how these laws are actually made. You're using the rate to find concentration at time t, and you're just using calculus to do that. And once again, you'll be given all these equations. The only caveat is that you do not know which equation is corresponding to which. So you need to know that, oh, if there's a natural log, it's first order. If there's like no reciprocal, if there's a reciprocal or like a fraction, that means it's second order. If there's nothing, just this equation, you need to know this corresponds to zeroth order. I was looking at the formula sheet earlier, and it seems like it's in order though. So like the the equations are listed: zeroth order first order next, and second order after, and it also gives you the half-life, which we'll talk about later. So what do these equations actually mean? It basically says the case rate the rate the thing used in a differential rate loss is the same constant here. K is a constant. T is like our x-axis, and A of t, concentration at time t, is like a y-axis. And we'll look at the graphs real soon. So this equation is basically saying the concentration at time t is a function of time. We've multiplied time by negative k because over time you lose some concentration as the reaction goes on, and you add it to your plus the initial concentration, which is A at time 0. So you start with this amount, over time you lose this much, and that's how much you have left at time t. First order, it's kind of like the same thing, but instead the y value can, if we want to linearize the graph, we'll talk about that as well when we look at the graph soon. But this is basically saying that a time t natural log of A of t is equal to the same thing here, negative k times t, plus natural log of the initial concentration. So this is like your kind of like y-intercept. It's kind of also your y-intercept. Want to think of it that way. Second order is a bit more confusing because notice how this term is positive. There's no negative sign before k, and we'll get to the reason why. It has to do with the fact there's a fraction here and here. But basically, 1 over concentration time t can be solved for using k times t plus 1 over initial concentration. So those are the three equations. Once again, you do not need to memorize them, nor know how to derive them. Could be helpful knowing some way how to derive them, or in case like you want to, just for fun, you want to understand like how the differential rate loss relate to this, but it's certainly not needed. So yeah, for graphs as well. So let's say we have zeroth order right now. We'll work on this first. Once again, the rate loss is going to be A at time t is equal to negative kt plus A initially. So what if we let the y-axis be A at time t, the x-axis be t? This is basically the same format as a y equals mx plus b. If you're currently taking like a physics class right now, you may know that this is like linearization. So we're trying to make a straight line by setting variables x and y to parts of other variables. So a of t is corresponding to y, and then x corresponding to t would give us just a line. So, and then since the slope is negative, we know that the line is going to be decreasing. And initially it starts with a positive concentration. So we start over here and we go down, and then we have a slope of negative k and an intercept of A of 0. So initial concentration. So this is basically if we have to plot concentration over time and you don't know what the order is. If you see something like this, when you plot A at time t and t and you notice a straight line, then this is just going to be zeroth order. And the reason why it's zeroth order, why this just produces a straight line, is because the rate is actually constant. The rate is just k times the rate of disappearance. This is how fast this is decreasing. This is basically constant because k is a constant. So each second you're losing this amount. So it's just going to be a straight line. The slope is constant. So first order is going to get a bit more complex, but first order is natural log of A times t is equal to negative k times t plus natural log A at initial concentration. You can also use logarithm properties to manipulate this equation a bit to get to move initial concentration to the left side and equal it to negative k times t. And then you can also use another property to make this become a fraction. So you can also use this as well. Now for graphing, you want to use this because it shows instantly what your x value is and your y value to graph is. The equation for a straight line is y equals mx plus b. So naturally, we want y to be natural log of A of t, so we can make a straight line. So we'll do that. So ln of A t, and then over time. Slope is still going to be negative here. So let's go down. The intercept this time is going to be ln of a 0. And the slope is still negative k again. So what's the point of like knowing these graphs? Well, in some problems you'll be given a table where you have concentration over time. Once again, they'll ask you guys, what order reaction is this? So what you want to do is you want to plot three graphs. You want to plot the AT over time, L natural log of AT over time, and it will get to the second order equation real soon, and that one. But basically, you want to see which one produces a straight line. So if it's this, if you get a straight line by plotting ln natural log of a of t over time, then you will know that this is first order because first order reactions correspond to this graph. So that's why it's important to know the graph of each order reaction. And you'll always see this equation in a formula sheet. So all you have to do is just linearize it and graph it in case you ever forget which one should be y and which one should be x. So second order is going to be a bit, this is going to be like the oddball kind of, and there's a few reasons why. So second order is just giving us reciprocal of a concentration at time t is equal to k times t plus 1 over initial concentration. So the main reason why here we don't add negative sign um, next to k is because actually when you increase the denominator, the fraction decreases in value. Like 1 over 2 is less than 1 over 3, kind of like that. So actually, as time increases, the denominator will actually decrease, meaning that this whole expression 1 over a at time t increases. So the y, if we linearize this, so y equals mx plus b, as x increases, as time increases, y actually increases as well, even though because a at time t decreases. So let's say a of t starts at 1 at time 0. Then let's say a of t becomes 0 0.5 at time equals 1. If a of t is 0.5, then the denominator is 0.5. So 1 over 0 0.5 is equal to 2. So this actually increases. So that's why the slope needs to be positive here. Once again, you'll be given the formula sheet. All you have to do is just linearize this. To graph it, you may have guessed it, the y-axis needs to be 1 over concentration at time t over time. And then slope is just going to be positive k. So that's why we have a straight line that actually increases this time. The other two graphs, the slope decreases. But here, the slope will increase and the intercept is going to be 1 over initial concentration. So those are your three graphs. And so that's basically the gist of integrated rate loss, being able to find how much concentration at a given time in a chemical reaction. For all of these, you will only have to deal with one reactant. Multiple reactants actually make this like really complex, and the AP test will only need you to know the equations, how to use these equations for zero, first, and second order reactions. And obviously no calculus is needed. So the next part of this lesson is half-life. So you probably have done this in your pre-calculus course or algebra 2 even, when you have like a radioactive element like uranium-235 and you want to see like it tells you like it takes 3 hours to for its half-life. That basically says that after 3 hours there'll only be half as much uranium. So if that's like 500 grams initially, 500 in a, that means 3 hours later you'll only have half as much, which is 250 grams of uranium. And then another 3 hours pass, we'll only have 125 grams of uranium 235. So this is your first half-life, and this is your second half-life. And half-life is basically, in a chemical context, is denoted as T 1/2 subscript. It's the time it takes for the concentration to drop to half its value. So if you start with X, for concentration to drop to half its value. And that basically means 50% of what we start with. So if that's like 5 grams of 5 5 moles per liters initially of a um, H2O, we want to see how long it takes for the H2O to decrease to 2.5 moles per liters. So here, I believe on the AP Chem test, that you will only need to like answer questions regarding first order reactions, but in the notes we were given like equations for zeroth order and second order, so I'm just going to go through that as well. First order reaction, it's actually given in the formula sheet, but I couldn't find like zeroth order and second order reaction half-lives in in the formula sheet. So not to worry though, because that's actually a nice trick we could find if we ever forget the half-life of something. That's actually a nice trick we can use. So let's say we want to find the half-life of a zeroth order reaction. Well, then you'll have this formula from your AP formula sheet that you can use. So if you want to find the half-life, you basically want to find how long it takes for um, AT, so the concentration at time t, to be half as much as the initial concentration. So you have a formula for A of t. So you would just intuitively plug in A of t. And after some simplification, you get negative 1 half A0 is equal to negative K times T. So solving for T is equal to, I'm rushing this up just a bit, but you can try it out algebraically and see that this is correct. T is equal to, well, this is half-life, so T1 over 2, since we're solving for something. So T1 over 2 is going to be initial concentration over 2 times K. So this is your half-life. First order reaction, um, this is going to be use a bit more math, but since you're already given the equation in the formula sheet, I won't go to deriving it, but it's just going to be 0.693 over K. And what is 0.693? 0.693 is actually equal to negative ln 1 over 2 as K. We just use 3 sig figs, I guess, on the equation sheet, so I'm going to do that here. Um, this is for first order. For second order, I believe the equation is 1 over A at time t minus 1 over A0 equals K times T. Once again, we want to substitute AT as 1 half times A0. So we get, or after some simplification, you get 2 over A0 minus 1 over A0. So same denominator, we can combine these two, equals K times T. So K times T is equal to 1 over A at time 0. So just to make sure, the half-life is going to be 1 over K times A0. This is second order reaction. Okay, so those are your 3 half-life equations. So just to summarize, um, A0 by 2K, um, 0.693 negative natural log of 1 half for first order, and second order, this is 1 over K times initial concentration. So now that's actually something important to notice for zeroth and second order reactions, also for first order reactions, but when A0 or initial concentration is used in a calculation, the concentration of A at the beginning of the half-life, so not necessarily the in very start of the reaction. So sometimes the problem might ask you like, what is the second half-life? So given a concentration over time, so let's say this is zeroth order, and you have just this like decreasing line. So for the first half-life, it's just going to be the time it takes for A0 to become 50% of what we started with. So around here, this is around 50%. So this is the amount of time it takes is your first half-life. The second half-life is going to start from here, and it's going to say how long it takes for this to be half of this. So around here. This is going to be corresponding to 25% actually of your initial value. And this is important to know. This is your second half-life time. It's not cumulative. So this is not the second half-life. It says this. And then similarly with here, this is going to be a third half-life, and then so on. So that's why it's important to know when we want to find like the second half-life, we need to start from the amount remaining at the end of the first half-life, and then go from there. So what do I mean by that? So if we have like, we want to find the first half-life of A0, concentration A, and we are given A0 initially is going to be 500. Let's just do good number. Let's actually just do 8. And k is equal to 1, just to make stuff simple. The first half-life, you can just plug in the initial value of A0 and then k. So 8 by 2 times 1 is equal to 4. So it actually takes 4 seconds. So 4 seconds. That's your first half-life. It takes 4 seconds to go from 8 moles, 8 moles per liters to 4 moles per liters. So second half-life, this is going to be a bit different. You need to start with how much you have left. So after 4 seconds, you lose half of the concentration. So you start with um, 4, 4m actually. So then you can just plug the equation in. It's going to be 4 over 2 times 1, which is equal to, let me put it on screen, 4 over 2 times 1, which is equal to 2 seconds. So the second half-life actually takes half as much time. So it's going to be 2 seconds. So basically half-lives, the length varies for the 0 and second order reactions because there's the initial concentration here. What you have to remember is that you need to use the correct value of the concentration for whenever A0 is there. So for first half-life, you can just use the very initial concentration, but for second and so forth, you have to start with the end of the amount of concentration left at the end of the previous half-life, like what we did here. Same thing goes for second reaction. However, notice in the first reaction that actually over time this stays constant. K is always constant. So your half-lives are always constant. That's something nice with the property that of natural log actually. So basically if we actually graphed like A0 over T, like not the linearized version of it, you would notice that the half-lives would actually stay the same. So don't confuse this with zeroth order, but if we didn't want to linearize the graph, you would get something like this, I believe. It needs to be exponential. But basically, the half-lives all have the same length. So this is one half-life, this is two, the second half-life, third half-life, and then so on. Notice how all of them have the same length because it's exponential. And remember, this is not the linearized version. For first order, you need graph ln natural log of a of t over time. So here's a tip. If you want to figure out order, but you were only given half-life data, if the half-life doesn't change, so if HL doesn't change, it's going to be first order no matter what. And then all nuclear decay reactions, so all nuclear reactions, like the uranium example, all nuclear decay reactions are first order. And you remember this from pre-calc again, right? It's actually exponential. You would like do like 2 to the power of t over 2, well, 1/2 to the power of t to the 2 times initial, like 500 grams, something like that. You would have exponential equation. So it's going to be first order. All right, that's pretty much it for this lesson. This is kind of big because it introduces two major topics, integrated rate laws and half-lives for each. And there you're given a bunch of equations, but I think what you need to know is a zeroth and second order reactions because they are not given in the formula sheet. And they could be easily derived once again um, by using the integrated rate law and setting A at time t to 1/2 initial concentration. The only thing I would say to be careful of again is notice that if you're trying to find the second half-life for stuff that's not the first reaction, you need to be careful about what value of A0 you're using. You need to be using the value given at the end of the previous half-life. Also, you'll just be finding the answer to the first half-life again and again. For zeroth and second order, the half-life varies. For first order, the half-life stays the same at this rate. So once again, find just it'll ask you questions will ask you like find the first two successive like half-life rates. You would find the first half-life, you'll find the amount of concentration remaining after that half-life is over. So like 8/2, that's 4. Second half-life, you start with 4, you see how long it takes to reach 2 concentration of 2 using this formula. K is going to be 1, so 4 2 times 1, 2 seconds. And if you had to find the third half-life, for example, you would start with 4 divided by 2, so 2 concentration of 2 moles per liters, and then you just use this formula again. Similarly with second reaction. So that's just something I'm emphasizing because it's pretty easy to forget. Thank you.